So today we're going to start learning about Chapter 6, Energy Relationships in Chemistry. And we're going to skip a little through the chapter. We're going to start with calorimetry, which is the measure of heat changes. And we need to know some different variables first. So we're going to learn some new vocabulary. We have this variable Q, which represents heat flow. There's a new variable S, which represents something called the specific heat capacity. And the specific heat capacity is the heat needed to increase the temperature of 1 gram of a substance 1 degree Celsius. So it's how much heat you need to make something like 1 gram of water go from 28 to 29 degrees Celsius. Or how much heat you need to make 1 gram of copper go from 5 to 6 degrees Celsius. How much heat you need to make 1 gram of a compound have its temperature go up by 1 degree Celsius. And then there is this new symbol, the triangle. Triangle means delta. So this is delta T. Delta T is your final temperature minus your initial temperature. Now we have an equation. Q is ms delta T. So heat flow is equal to the mass of a substance times the specific heat capacity of a substance times the change in temperature of the substance. So let's do a problem. Here we go. Here's our problem. And when we are solving heat capacity problems, we want to set up a little chart. You have to recognize that you are doing a heat capacity problem. Whenever you see S, you should think, oh, Q is ms delta T. That's the equation that should come to mind. So we're going to have a little chart of data that we have over on the left. So what are we given? We know we have 466 grams. Oops. And we also know we're going to need to use the equation Q is ms delta T. So what would the grams be in that equation? Right, mass. What else do we have? 8.50 degrees Celsius, 8.50 degrees Celsius. Now that's a temperature. Is it our initial or final? It's going from 8.5 to 74.6. So we're starting at 8.5. Hopefully you realize that doesn't look very good. That is our TI for T initial. Then we also have 74.60 degrees Celsius. And that's the temperature we end at. That would be our TF. Calculate the amount of heat. So heat is Q. And we don't know what Q is, absorbed in kilojoules, kJ. So now we have this new unit, a J. J is a joule. kJ would be kilojoules. So we want to calculate the amount of heat absorbed in kilojoules by the water. And notice we're also given our specific heat capacity. S of water is 4.18. joules per gram degrees Celsius. And it looks like we have enough information to solve our equation right here. We're just going to plug in. So Q is 466 grams. S right here, 4.18 joules per gram degrees Celsius. T final right here, 74.60 degrees Celsius. Minus T initial, 8.50 degrees Celsius. And you plug that all into your calculator and you get 12,000, nope, hold on, 129,000 joules, not 12,900. But the question said, find the heat absorbed in kilojoules. So I have to convert these joules to kilojoules. And there are 1,000 joules in 1 kilojoule. hopefully you remember kilo means 1,000, so we have 129 kilojoules, and that is our answer. Now we're going to move on to heat transfer. This is where heat is going to be transferred from one substance to another. When we have heat transfer, we have Q1 is negative Q2. So the heat flow for one substance is equal and opposite to the heat flow for the second substance. Q1 is negative Q2. And we already know Q is ms delta T, so we just plug ms delta T in for Q of substance 1 and Q of substance 2. What does that look like in a real problem? Well, here's our problem. And in this problem, oops, sorry. Okay, in this problem we have lead and we have water. So the reason why you know this is a Q1 equals negative Q2 problem is because you have two separate substances. So we know we're going to have Q1 and Q2. So instead of writing Q1, we'll just write Q of lead and Q of water, H2O. That worked out quite nicely. And we know that Q of the lead will equal negative Q of the water. And let's write down all the information we can find about each thing. So this lead pellet has a mass. We're going to put this over on the lead side. Mass is 26.47 grams. It's at, that would be our initial temperature. It is at 89.98 degrees Celsius. We put it on a calorimeter containing 100 milliliters of water. Oh, we got to go over to the water side now. Now we know we have 100 milliliters of water, and we have the density of water. We need ultimately to get to the mass of the water, so we're going to have to multiply this by the density, 1 gram per mil, to get the mass of the water. We actually had one more decimal place in there. So we have 100.0 grams of water, and that is our mass of water. Okay, so we've used this already, and we've used this piece of data. The water temperature rises from, so we start at T initial is 22.5 degrees Celsius. Oops, oh no, that's correct. We go from the 22.5 to 23.17 degrees Celsius, and that would be our final temperature. What is the specific heat of lead? S of lead is what? Now, in the previous problem, I gave you the specific heat of water, and this would be given to you in a problem. So we already know the specific heat of water. It's 4.18 joules per gram degrees Celsius. And we actually know something else about the lead. So this T final, the final temperature is the same. When we have a heat transfer problem, the final temperature of any substance in the solution is the same. So this T final will also go over here. So T final for the lead is also 23.17 degrees Celsius. Okay, so we have our equation. Let's extend the page. That Q lead equals negative Q water, or ms delta T for the lead is negative ms delta T for the water. And if you check, you'll find you have all the information you need and only one variable is missing, and we can solve this equation for the missing variable. So I'm going to plug everything into this equation right now. Okay, I plugged everything in. You might want to pause the video and try to plug this in yourself and solve the whole thing for us. You can also just follow along. So the right side is going to be negative 280.3 joules, because the grams cancel, degrees Celsius cancels, So we're left just with the joules. And then if we solve for just isolating S, we get S is negative 280.3 joules divided by 26.47 grams times negative 66.81 degrees Celsius. And when we calculate that all out, we get 0.158 joules per gram degree Celsius. Okay, one important thing about these, just some things that people often miss. This negative sign right here, Q lead is negative Q water, or the equation Q1 is negative Q2. Never forget, oh dear, the computer is acting up. I think we're good now. You never want to forget this negative sign right here. And then in our equation, when we're solving for S right here, we have a negative and a negative, which cancels to give us a positive specific heat capacity. And notice our units end up at joules per gram degree Celsius. So you always have to keep track of all of your units in these problems. Okay, why did I keep only 3 sig figs? Because right here, when we do our 23, oh, oops, hold on, sorry about that. When we do our 23.17 minus 22.50, actually, we should only keep 2 sig figs. When we do this subtraction right here, we end up with 0.67 degrees Celsius, and that subtraction leaves us with only 2 sig figs. So actually, our final answer should be 0.16 joules per gram degree Celsius. The sig figs get a little bit confusing in these problems because when you're adding and subtracting temperatures, sometimes you lose a sig fig. When you can convert to Kelvin, sometimes you gain a sig fig. Speaking of Kelvin, you do not need to convert to Kelvin to do these problems because you are doing subtraction of a temperature here. And when you subtract a temperature from another temperature, adding the 273 to the temperatures cancels itself out. Okay, one more problem. We got 58 grams of lead at 75 degrees Celsius, and that's placed in a calorimeter holding 60 grams of water at 12.2 degrees Celsius. Find the final temperature. Well, we have 2 substances. We've got lead and we've got water. So we're going to have a Q1 is negative Q2, Q lead is negative Q water. So we'll set up our lead information and our water information. Hi, wait a minute. So we had some visitors to the science building, and now I forgot where we are. Okay, I was saying we have 2 substances, we have lead, and we have water, and we're going to figure out what data goes where. 58 grams of lead, that's going to be, hopefully you recognized, our mass of lead. And the lead is at 75 degrees Celsius. Initial or final, ladies? Initial. 75 degrees Celsius. We've got 60 grams of water. 60 grams of water. The water's at 12.2 degrees Celsius. Initial or final? Initial. And what's the grams? The mass. Okay. Find the final temperature. Of what? What are they talking about? Find the final temperature of the lead or the final temperature of the water? Do you remember from the last problem? The final temperature is the same for both substances. So, TF equals question mark, and it's the same as the TF over here. It'll be the same T final, same variable, we don't know what it is. Now, specific heat capacities. From the prior 2 problems, we already know the specific heat capacity of water is 4.18 joules per gram degree Celsius. And the specific heat for lead is, I'm actually going to look this up in a book so I can have more sig figs. Okay, so I just looked this up on the internet. This is very interesting. It's actually 0.127 joules per gram degrees Celsius, which is very different from the answer we got in the previous problem, which was a problem from your book. So apparently the problem in the book had a very impure piece of lead that was put into the water. If you're wondering what I'm talking about, in this problem here, we found the specific heat was 0.16 joules per gram degrees Celsius. So that's not all that close. Well, it's not that far, but it's certainly not what we're finding on the internet, 0.127 joules per gram degrees Celsius. So apparently the book problem used some impure lead. Okay, back to the problem at hand. So we have our equation. Q lead is negative Q water. And now ms delta T of the lead is negative ms delta T of the water. We'll plug in our values. You can pause and try to solve this whole thing out. I'm going to put it up in a moment. Okay, and notice I put an X for TF just because often students are thinking about algebra. It's up to you. You could leave the X as a TF symbol. Let's look at our units here. The grams cancel. The grams cancel. Now, the degrees Celsius on the left and the degrees Celsius on the right can cancel, and the joules on the left and the joules on the right are going to also cancel. Students tend to like to multiply and then distribute. I want to show you how I solve this. Okay, I like to get the numbers in front of the parentheses on both sides and then divide both sides by the smaller number, dividing both sides by 7.366. This simplifies my problem. I only have to distribute once. Oops. Okay, so now I need to distribute the 34.05. Okay, and again, be very careful with your positives and negatives. I had to distribute this negative sign right here also, so I get a positive over here. So now I have 75 plus 415.41 is equal to 34.05x plus x. So I get 35.05x is equal to, wait, these were degrees Celsius. Okay. Now I divide both sides by 35.05. And I get x is equal to 13.99 degrees Celsius. But now I have to check all my sig figs. Let's see. Let's look up here. So at most I could keep 3 sig figs, because I'm just looking and I'm seeing I've got 3 sig figs in my numbers, but I was also dealing with some addition, subtraction, so let's just check. I've got tenths place, so I can keep my answer up to the tenths place. So this becomes 14.0 degrees Celsius, which happens to be 3 sig figs. That's my T final. And that's it for today.